Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. The study of condensed matter can yield insights into fundamental physics. Metamaterials, constructed using discrete engineered building blocks, can open up study of some interesting phenomena. One type of metamaterial has the potential to revolutionize how we understand the universe and could hold the key to studying dark matter. Professor Alexander Dmitriev from the University of Gothenburg in Sweden has been studying metamaterials for decades. In collaborative work, his team has devised a computational model of a metamaterial that exhibits the Telegon effect, also known as the magnetoelectric effect, when exposed to visible light.
What's the magnetoelectric effect? The closest relative is, of course, the chirality. If you think of, matter that is sort of structurally non-symmetric. But of course, the time symmetry holds. You go back and forth. It's the same chiral effect that you experience when the light is transmitted through the medium. So now imagine that you not only break the symmetry, the parity, but also the time symmetry, that is the reciprocity. So, going here and going there creates a different effect. And that actually is also close to what people experience when you look at these magneto-optical materials. It's like basically an isolation. The light passes through a medium, and let's say the polarization rotates a certain way, but when it passes backwards, the polarization rotates further, and you do not cancel the effect, but you make it stronger by going back and forth. So that is the non-reciprocity in transmission. So then imagine these magnetoelectrical materials, they combine both somehow. And that, of course, leads to very cool and sort of non-intuitive consequences.
Professor Dmitriev's team built computational models of the metamaterial. The building blocks of this metamaterial are comprised of disks of silicon, 150 nanometers in diameter, supporting a cylinder of cobalt. These building blocks are randomly distributed in space. The size and properties of these nanocylinders is important for promoting the Telegon effect. When silicon is in layers just a few hundred nanometers thick, light can effectively get trapped, causing resonance. While silicon was chosen because of its high refractive index, cobalt was selected because it can spontaneously magnetize.
We pick up the electric component of light, and then by manipulating it inside this unit, we create a magnetic dipole, which is also in phase with the incoming electrical dipole. I mean, the whole concept of Telegon material, as it was imagined by Bernard Telegon, it's actually an electrical dipole that is glued physically to a magnetic dipole, like to a magnet. So there are two dipoles, they are collinear and they are in phase. So that is what we realize now for the visible light, but of course you need this initial static magnetic moment. So it's either you sort of magnetize every of these units, just going around, magnetize them one by one, and you can do that if it's the microwave. But what we wanted is a fully isotropic matter where everything is mixed up. This is absolutely crucial to have that. We do not apply any external bias. We just make materials out of cobalt, and then it spontaneously magnetizes.
The structure is surprisingly simple, but the challenge is in extracting the Telegon parameter from the simulations. This dimensionless parameter describes the magnetoelectric effect, which is a coupling between electric and magnetic fields. In initial simulations, the Telegon parameter was small, but alterations to the structure led to an increase in its value, enough to give the proposed metamaterial very real applications once it is produced experimentally. So the metamaterial has applications in areas such as improving the efficiency of solar cells, creating one-way glass, or improving lasers. But by developing a metamaterial with a design founded on fundamental physics, Professor Dmitriev's team will effectively be able to replicate astral bodies in the lab.
The equations that describe Telegon matter are the same in quantum field theory that describe the accidents and dark matter. It's a bit cumbersome to do experiments in space. So lots of time people were trying to simulate what could happen there just on the optical table by making materials that would behave a bit similarly to celestial bodies. Here, mathematics holds and the physics holds. That was the prime motivators to have these Telegon materials. because they are described by the same electromagnetic equations as the dark matter. So it becomes sort of straightforwardly available experiments which are completely unthinkable in the realm of the real universe.
This work was published in a recent issue of Nature Communications. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.